All right, so this, of course, the rings are the obvious thing that is observed about Saturn. The rings are made of icy material. There are these tiny little moons that are in the that actually help to shape the rings. They're called shepherding moons. They're very thin. The rings are extremely thin. We, we actually passed the Cassini spacecraft through the rings towards the end of its mission. Um, and there's a reason that the rings extend out about two. So if you look at the radius of Saturn, and then you go about 2.44 times the radius of Saturn, that's where the rings end. And there's a very good reason for that. We're going to go into that right now. So the rings, there's what's called the A ring, which is this part where you can't really see. There's a little gap right there. That's called the ankle ring, the ankle gap. So that's the A ring, and then comes the B ring, and then after after the Cassini gap is the C ring. There's actually other rings. There's rings outside of this. I think it goes up to like G or something like that, if I remember correctly. All right. So you can see this better. So this is done in false color to kind of emphasize it. That the rings are not made of solid material; they're ice, and it's very very thin. Um, so this right here is the A ring. There's the Anki gap. Um, this is the B ring, and there's the Cassini gap. Very, very even with just a moderately sized telescope, you can see the Cassini gap. This one, this gap right here, the ankle gap, uh, or the Anki gap, is very difficult to see from the Earth. You need a pretty large telescope, like the kind they build on top of mountains, to be able to see that one. All right. Anyhow, so it's mostly um, uh, water ice. That's what and that's why the rings are visible from the Earth, right? Is they reflect sunlight very very well, and they're easily seen, even with a small pair of binoculars. In fact, Galileo uh, saw the rings. He didn't know what he was looking at, but he did record that there were some kind of bulges from the center of Saturn, and that turned out to be the rings. Um, all right, yeah, about a generation or so. I think it was a generation or so after Galileo. There was a guy who first detected this, or built a telescope large enough to see it, and that person, of course, was the astronomer Cassini, who the spacecraft many years later, centuries later, was named after this guy Cassini. Sometimes we'll see that there'll be like dust particles that'll fall onto the rings. They kind of look like spokes on the rings. Um, it's just dust from from material. All right, so now one of the things that was detected by the Cassini spacecraft. This was a great discovery by the Cassini spacecraft in the 2000s. I forget exactly when it was. What are called the shepherd moons. And so the shepherd moons, you can kind of see these little ripples right here, and that's the effect of gravity. Remember, this is not a solid. It's just a whole bunch of little tiny um, ice particles, anywhere from centimeter size to maybe a couple of meters across. And these moons are maybe hundreds of meters in size. And so what happens is as the shepherd moons orbit, that they'll cause these little ripples But the ripples actually have another effect, and that is to keep these little rings and ringlets. The individual ones are called ringlets. It keeps them in order. Like a shepherd dog would keep the flock in a line, and so that's why these are called shepherding moons, is because they keep these ice particles in a nice ring shape. But by the way, we don't think that the rings are a permanent feature of Saturn. That maybe the rings formed. You know, we don't exactly know. It could have been hundreds of millions of years ago, but certainly we don't think that the ring system is billions of years old. That's pretty unlikely. Um, just looking at the dynamics of the rings, it wouldn't last that long. Um, all right, so now we're going to get to the reason that the rings are the shape that they are and the size that they are. It has to do with this thing called the Roche limit. All right, so this is a limit that this mathematician named Roche discovered. I think it was like 2 centuries ago. He worked out the mathematics of this, and so what he determined is, sorry, let's go to the next picture right here. This is really nice. So if you take a planet and you take a moon, and if the moon is made of the same material that the planet is made of, that's really important, by the way, because the Roche limit is different if it's not. But if the moon and the planet are made of the same thing, um, that is, the density of this object and the density of the planet is roughly the same, then there comes a point when the planet, I'm sorry, when the moon experiences tidal forces. Well, there's always tidal forces. I mean, even if the moon is way out here, there's tidal forces. That is, the force on this side, the gravitational force on this side of the moon is greater than the gravitational force on that side of the moon. And that's really what the tidal force is. But what Roche proved convincingly is that when a moon is, again, it's got to be made of the same stuff that the planet is made of. When it reaches a point that is within 2.4 times the radius of the planet, or 2.44 times the radius of the planet, that's called the Roche limit. And once the moon crosses that, or if it crosses that, what'll happen is the tidal forces will rip the moon apart. It'll tear it completely apart. There's no way for the moon to stand up against the tidal forces. All right, and in fact, that's what has happened to form Saturn's rings. Right, there's some icy body got too close to Saturn and tore it apart, and that's another reason that we don't think the rings are permanent. Now, notice this last line right here. So we're talking about objects that are, for the Roche limit to apply, it has to be something that's held together by gravitation. So it's made of the same. It's made of the same material that the planet is made of. That is, they has the same density as the planet, and it's large enough to be held together by gravity. All right. So now, what about things that are smaller than that, like something? Asteroids are different sizes, so it's hard to just have a grand category of objects. But like the shepherd moons are smaller than most of the asteroids. I mean, there's some asteroids that are smaller than the shepherd moons, but on average, let's say the shepherd moons tend to be smaller than that. And what that means is they're too small to be held together by gravity. That there's actually chemical forces that hold those moons together. So those moons can exist within the Roche limit because they're not held together by gravity, right? So the tidal forces won't tear them apart. So the shepherd moons, there they are, can certainly exist within the bounds of the Roche limit. But of course, most of those particles are coming from some icy body that got ripped apart, right? By the but because of the Roche limit, right? So because its icy body got within the Roche limit and got torn apart. All right. So anyhow, all right. So Saturn has several large moons, and many small ones. So it's kind of like a little mini solar system, just like Jupiter. These things going around Saturn. There's one really large moon, and um, and that starts to get about the size of the Galilean moons. All right, and that here, let's look at these. That moon is called Titan, and Titan is so large that it actually it is like I said about the size of the gal. It's not the largest moon in the solar system, but it is a very large moon, and it has its own atmosphere. Right. This is why when the Voyager 1 spacecraft got there in the 1980s, it took a different path to study. Remember, the Voyager 1 the Voyager, both of them were supposed to go to Uranus and Neptune. Now, Voyager 2 did go to Uranus and Neptune. That's why we know about those worlds. But the Voyager 1 it was decided to deflect it so that we could study Titan a little bit more, in a little bit more detail. All right, so these other moons are always are would be categorized as medium-sized moons. The rest of them are really tiny. All right, so of the medium-sized moon, Mimas is the smallest one. Sometimes this is called the Death Star moon. If you ever watch Star Wars, it kind of looks like the Death Star. It's a really odd moon in that it looks like it was torn apart and then reassembled. Um, there's Enceladus. We'll have a lot more to say about Enceladus. This is a moon that has liquid water under the surface of a very icy surface. There's Dione, Iapetus. Iapetus has this strange dark material, which turns out to be what are called tholins. They are organic molecules that make this up. Tethys is another one of the medium size, and Rhea is the largest of the medium sized moons. So as I said, Titan is the biggest one, and we're going to study that in a lot more detail. Hold on, just let me see. Let me make sure. All right, so let me just say a little bit about Enceladus. It could be, and I'll return to Enceladus in just a little bit as well. But Enceladus turns out to be one of the most interesting moons in the entire solar system because, like, Europa that goes around Jupiter, it has a liquid ocean and underneath its surface, and that liquid ocean may have life forms. Microscopic life forms, we think, but possibly life forms could exist in the oceans of Enceladus. What else? There are geysers, saltwater geysers coming from the South Pole of Enceladus, and we actually passed the Cassini spacecraft through those geysers and sampled the water and measured the salinity, how salty that water was. That was another thing that we did. All right, so We'll look at Titan now.